Good morning, everyone. My name is Diego Guerrero, and I'm a member of the Stain Monogastric Laboratory as a PhD student. Today, I will present our research titled Influence of 25-hydroxycholecalciferol and Dietary Calcium and Phosphorus on Calcium and Phosphorus Digestibility by Gestating Sows. This research was presented in the Midwest Annual Meeting in 2026. Calcium and phosphorus are essential minerals because their fundamental role in bone development, metabolic processes, just like energy metabolism and cellular signaling, and reproductive performance, supporting successful gestation and healthy offspring. Because of these important functions, the paper of the mineral supply is critical. When the dietary supply of calcium and phosphorus is adequate, the sow can maintain a careful balance between her own mineral requirements and developing of fetuses. This balance helps to maintain the health and bone integrity of the sow, resulting in healthy and viable pigs. However, when dietary supply is insufficient, this balance is lost and breaks the system. In this situation, the sow must mobilize calcium and phosphorus to support fetal growth, compromising maternal health, negatively affecting sow longevity and productivity. One challenging fact is that sows have reduced calcium and phosphorus digestibility. To illustrate this point, I'm presenting this chart from an experiment where gestating sows and growing pigs were fed the same diet. And as you can see, growing pigs had 78% digestibility of calcium, whereas in sows, only 26%, with a similar pattern in phosphorus digestibility. Because the reduced digestibility regulation of calcium and phosphorus metabolism, one of the key regulators of calcium and phosphorus metabolism is vitamin D. This vitamin is fully recognized by participating in calcium and phosphorus homeostasis, facilitates absorption of these minerals, and plays an important role in bone metabolism. But also, it's involved in bone health, immune system, and muscle development. However, vitamin D3 must be converted into an active metabolite. The first hydroxylation occurs in the liver, where it turns to 25-OHD3 by the enzyme 25-hydroxylase. Then, in the kidney, it's hydroxylated into the active form 1,25-dihydroxyvitamin D3 by the 1-alpha hydroxylase. Usually, vitamin D3 is supplemented in the diets, but by adding 25-OHD3, we can skip the first hydroxylation and go directly to the second one and get into the active form. With all this in mind, we aim our study to test the hypothesis that increasing dietary calcium and phosphorus levels, as well as supplementing 25-OHD3, will improve the apparental total tract digestibility, standardized total tract digestibility of calcium and phosphorus in late gestation of sows. To test this hypothesis, we conduct a randomized complete block design with a factorial arrangement 4 by 2, where the factor were 4 different levels of calcium and phosphorus and the addition or not of 25-OHD3. We fed the sows from day 45 to day 90 with this calcium and phosphorus ratio. And from day 91 until farrowing, we adjust the calcium and phosphorus ratio considering the differences between dietary treatments. We conduct this experiment using 64 multiparo sows, and as I mentioned before, it was a randomized block design with a factorial arrangement with 8 blocks, 8 sows per block, 1 sows per block per diet. The feeding program consisted in 2 phases, 8 diets by phase, 4 concentration of calcium and phosphorus, with or without 25-OHD3. To determine mineral digestibility, fecal and urine samples were collected for 4 days. During this period, sows were housed in individual crates with 5 days of adaptation. We calculate the apparental total tract digestibility and standardized total tract digestibility of calcium and phosphorus during late gestation. We evaluate productive performance such as body weight changing, litter size, and litter weight after farrowing. And we measured 25 hydroxyvitamin D3 concentration in plasma from sows as well as newborn tissues, including kidney, liver, and jejunum. All the data was analyzed using linear and quadratic contrast to evaluate the effects of increasing calcium and phosphorus and the interaction with 25-HT3. So let's move on to the results. But first, I would like to explain how to read all the charts I will present in the following slides. On the x-axis, the 4 increasing dietary concentration of calcium and phosphorus, and the blue bars represent the diets without 25-OHT3, and the orange bars represent the diets with 25-OHT3. As expected, calcium intake increased as dietary calcium and phosphorus increased. Insignificant linear effect of calcium and phosphorus, but the supplementation of 25-OHT3 didn't have any effect. The calcium excretion increased as dietary calcium and phosphorus concentration increases, but 25-HC3 slightly reduced fecal calcium losses, suggesting an improvement in calcium utilization or retention. In contrast, calcium excretion in urine remained relatively low across treatments. These slightly greater values at lower mineral concentration may reflect reduced calcium retention when phosphorus availability limits bone mineralization. Similar to calcium intake, phosphorus intake also increased as dietary calcium and phosphorus concentration increase, with a linear effect. Following phosphorus intake, phosphorus excretion in feces also increased as dietary and calcium phosphorus concentration increased, and also the supplementation of 25-HT3 reduced phosphorus fecal losses, improving phosphorus utilization. In contrast of calcium urine excretion, phosphorus excretion in urine was relatively low. However, it increased as dietary calcium and phosphorus concentration increased, resulting in a linear effect. After evaluating intake and excretion of calcium and phosphorus, we can move on to the digestibility of these minerals. So, in this first chart, you can see the apparental total tract digestibility of calcium, where you can observe that the lower digestibility in some treatments suggests that higher calcium and phosphorus reduce the proportion of calcium absorbed, with 25-HT3 improves calcium apparental total tract digestibility. A similar pattern was observed for standardized total tract digestibility of calcium, with a linear decrease, and adding 25-HT3 enhanced the efficiency of calcium absorption in gestating sows, particularly when the mineral supplementation is low. With apparental total tract digestibility of phosphorus, there was no differences by increasing the calcium and phosphorus dietary concentration, but the addition of 25-HT3 improved phosphorus digestibility. After correcting for endogenous losses of phosphorus digestibility, it increased without showing response by increasing calcium and phosphorus dietary concentration, and also improving efficiency of phosphorus digestibility with 25-OHT3. This chart is a little bit different from the others, but it follows the same arrangement. The difference is that the bars with lines represent the concentration of 25-OHT3 in plasma from the sows at the beginning of the experiment, and by farrowing, sows with 25-OHT3 show greater plasma concentration, confirming that the dietary supplementation effectively increased circulating vitamin D3 status. For newborn liver, 25-HT3 concentration did not have a significant effect. Instead, a linear effect of the dietary calcium and phosphorus was observed, suggesting that the mineral supply may influence vitamin D status in the offspring. In contrast with the liver, kidney 25-OHT3 significantly increased by maternal supplementation, indicating the effective transferation of vitamin D3 metabolite from the sow to the upstream. In summary, increasing dietary calcium and phosphorus will increase mineral intake, which result in greater fecal excretion. At the same time, higher mineral concentration reduce digestibility of calcium. In addition, supplementation of 25-OHT3 increased plasma concentration in gestating sows, improving digestibility of calcium and phosphorus, and greater concentration in the kidney of the offspring, suggesting an effective maternal transferation of vitamin D3 metabolites. Finally, I would like to thank DSM Firmenich for supporting this research and also all the members of the STEM lab for their help during this experiment. Thank you for listening, and if you want to know more about our research, visit our website, STEM Lab Monogastric. Thank you.